In this section of the course, we're going to talk about the topic of improper integrals, which are basically integrals, but the limits of the integration, you know, the numbers that go on the integration symbol itself, usually involve infinity, okay? And so we're going to talk about that. Let's just do it by means of an example. You have the integral of 2 to the infinity, and we'll talk about what that means in a second, of this integral, 1 over x plus 3 to the 1/2 dx. First, you might ask, well, what the heck does that mean? Usually, you have an integral. Here's some function, and you're looking at the area between two points like this, and you're going to find this area, okay? Now, usually, if your integral is something like this, and goes kind of up like this, if you integrate from some number like 2, like we're doing here, all the way to infinity, the area that you calculate is just going to get bigger and bigger and bigger and bigger and bigger, and you're going to end up getting infinity for an answer, and it's not going to converge, is the term that we actually use. It's not going to actually equal a number. It's going to equal infinity. So usually you would think that if you integrate something off to infinity, you're going to get infinity. But it turns out that some problems, like some of the problems we're going to do here, what if the function starts high and then ends up going down low, 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 and eventually approaches 0 as you go off like this? Well then, if you start integrating from here, you're going to get a smaller and smaller and smaller and smaller and smaller area, and in some cases, even though you're integrating on forever and ever and ever and ever and ever and ever and ever, it's going down, approaching 0, so eventually you do end up what you call converging on an answer. So the answer might be 1, or it might be 2, or 3, or whatever. But in some cases, when you integrate to infinity like this, you can actually get a number instead of getting something nonsensical like infinity. And that's what this section of the class is going to illustrate. So how would you do this integral? Well, I would do it by substitution, and that would be x plus 3. So then du would just be equal to dx. Okay, because the derivative of this is 1. You can move your dx over. And so then, to do the problem, it would be 2 to the infinity, 1 over u to the 1/2, and then dx is equal to du, so you'd have this like this. Okay, and you could solve that integral. But don't forget that over here, these limits were in terms of x equals 2, and x is equal to infinity. So to actually pull it off, you need to convert to u. So if you put 2 into this, then over here you'll have u is equal to 5. 2 plus 3 gives you 5. And over here you'll have u is equal to, again, infinity, because if you plug infinity in, you'll get infinity plus 3, which is just simply a slightly bigger version of infinity. So you just put infinity there. And you'll have u to the negative 1/2 du, because you just move this up like this. This is very easy to integrate. It's 1 over 1 plus the exponent, which is 1/2, times u to the 1/2, evaluated at 5 to infinity. Just the limits that we calculated here. Okay, so then this will be 2 times u to the 1/2. Well, let's go ahead and write it. Let's write it in a slightly better form. Yes, we'll have 2 times u to the 1/2, evaluated from 5 to infinity. So to do this, we use that fundamental theorem of calculus. We plug in the top value, which is simply 2 times infinity to the 1/2, right? And we'll subtract off the bottom value, which is just simply 2 times 5 to the 1/2. Okay? So what you will have here, infinity, the square root of infinity, which is what this is still infinity. So you'll have infinity here. And then here you'll have some small number, 2 times the square root of 5 is what this is. Infinity, which is an infinitely large number, minus this pretty small number, is still going to give you infinity. So in this case, you say that this integral does not converge. Okay, you start out with an integral, you do it just like usual, you basically plug in the limits even if they are infinity, and if it comes out to something absurd like infinity, then you say, well, the integral doesn't converge. This would be an example of an integral that it approaches 0 in this case, because you can see it's 1 over some function of x, but it doesn't approach it fast enough, and so it doesn't actually converge. So that's what you would write on your test. You would say this integral does not converge. Okay, but you'll see here in the next problem that that's not always the case. In some cases, these integrals actually do converge. So let's do one of those right now. What if you were integrating from negative infinity to 1 of the integral 1 over 2x minus 3 squared dx? Okay? And then we said u is going to be equal to this in the bottom, 2x minus 3, so that du is equal to 2 times dx. du dx is 2, and then we move the dx over. Okay? So then dx is equal to 1/2 du. So when you do this integration, you'll have negative infinity to 1, and don't forget this is x. These limits are in terms of x. Okay? And you'll have 1 over u squared, because we defined u like this, but then dx we defined like this, so we'll have 1/2 du. Okay? So, in the end, you'll have 1/2 integral of u to the minus 2 du, but in order to do this, we have to change our limits of integration. If you plug in negative infinity into here, you'll get u is equal to, again, negative infinity. 2 times negative infinity minus 3 is just going to give you, again, negative infinity. And if you plug in a positive 1 in here, 2 times 1 is 2 minus 3 is u is equal to negative 1. So that's the upper limit. This should all be familiar from our other section on definite integrals. So you have 1/2, and to pull this integration off, it's going to be 1 over exponent plus 1 is negative 1. Negative 2 plus 1 is positive 1 times u to the negative 1, just like this, evaluated from minus infinity to minus 1. And so to simplify this, you'll have negative 1/2 times 1 over u evaluated, negative infinity to negative 1. And so then, in the end, you'll have negative 1/2, okay? We'll do it like this, negative 1/2, and you plug in the top limit times 1 over negative 1. We just plug this in here, minus evaluated at the bottom, which is negative 1/2 times 1 over negative infinity, like this. And so this is going to be negative times negative gives me positive 1/2, okay? And I'll have a subtraction here, okay? But inside here, I'm going to have negative times negative gives me a positive, but everything's divided by infinity, you see here, so this is going to be 0. Because you have basically 1/2 times, and then this over here, this becomes 0. Anything divided by infinity gives you a 0, okay? So then negative times negative gives you positive, and then anything divided by infinity gives you 0, so you have this. So in the end, because that goes to 0, in the end you have 1/2. So then this integral does converge, and it converges to the answer 1/2. So I'm not going to work any more of these problems because they're not that terribly different than what we've done before. But basically, you have an integral, and it's called an improper integral when one of the limits is infinity. And so then you just do the integral the same way we've done before, including transforming the integral limits themselves if you need to, if you do substitution. But in the end, when you plug it in, you plug in infinity as if it were another number. And I just showed you a case when it blows up and it doesn't give you an answer that converges. And in this case, I've shown you when in some cases the infinity can force you to 0, and so you can actually end up with a solid number. This would be an example of some kind of integral where it went down so close to 0 so rapidly that the actual area, even though you're integrating from minus infinity, I'm kind of drawing my graph a little bit wrong here, from minus infinity all the way up to a number, so you've got minus infinity on forever and ever and ever, and you're adding up stuff, it actually converges to a solid 1/2.